Yeah, I think we start. Welcome to the Q&A for the ISM lecture. I think we start. We are 12 people right now, but maybe a few more come in a little later. I have some topics for today. But before that, let me briefly ask whether there is, again, if there was any problems, if you had any problems with the lecture notes or the videos. I saw that I forgot to add chapter marks to the videos of the lecture 3, so I added them now. So if you rewatch the videos, you should have the chapter marks. And the new notes should also be online.
I have a question. Because viscosity dissipation, what is this exactly?
Viscous dissipation, what this means? Is this the question?
Can you repeat that again?
Is the question, what is viscous dissipation?
Yes.
Okay. Maybe somebody from the like from the audience here can help out.
Is it something about friction and the production of heat?
Yeah, find it. Yeah. So you are talking now about the turbulence chapter, I guess. Or was this already mentioned in the hydro part?
Yes, in the turbulence chapter.
Yeah, okay. Well, viscous dissipation is basically the point or the scale at which the motion of the fluid elements becomes basically random, because let's say you have a cup of coffee and you start to stir it with a spoon. So you induce some systematic velocity field in your cup of tea, and this motion and the motion of the cup induces the motion on the surrounding fluids elements, and this is then handed down to the other fluid elements in your cup of tea, and it creates swirls and turbulence eddies depending on how fast you stir your coffee on smaller and smaller scales. And we saw in the lecture that there is a cascade, so that when you look at large volume elements and small volume elements and even smaller elements, how much energy is basically in this turbulent element. Then this gets smaller and smaller and smaller and smaller, and at some point you enter the regime of Brownian motion. And this is what, as you mentioned, this is when friction basically, so viscous friction in the fluid elements basically dissipate the energy, and it turns into Brownian motion, and it is not some structure anymore.
Okay, I'm satisfied.
Yeah, this is meant with this dissipation scale. Okay. Good. So this was already like a topical question. Very good. So if there is no problems regarding the technique, then I wanted to remind you to fill out the doodle. I reposted here in the chat. If you want to have a graded certificate, so einen benoteten Schein, then you have to pick a presentation topic and give a 15-minute presentation. I saw that pretty much immediately 4 people, maybe I should. So it's 4 people right now that filled in. There's Frau Krasilowskaya, you wanted to do it already in December, so that's already in 4 weeks. So if this holds, then we should like talk briefly about the topic. I think you sent me an email also, right?
Oh, I didn't send an email, but I picked something already out. I want to do something about the paper about the dark nebula, globus, and protostars. And I think it was a 2-parter. There's also the paper about, from the Astrophysical Journal. I will do both. Is this okay?
Let me briefly check with the topic. So you were looking at the website, I guess?
Yes.
So, which is which topic was it? Bock, dark nebulae?
Yes, this one with the 2 papers.
2 papers, right? Yeah. So this is Banach, 1 paper from 1919 and 1 from Bock 1977.
Yes.
That's fine. Sure. If anybody, if not, if this is not conflicting with the pick of anybody else, let me see. I got an email. I can see this here. Okay, so we do this. Please tell me whether you have difficulties with accessing the papers from the links. So if then I just send them as PDFs. And so that's maybe something interesting for everybody. So if you want to do a talk, I highly suggest that we have a rehearsal before the actual talk, so that we meet maybe 1 week earlier via Zoom. And you basically give the presentation to me so that, and I can give feedback. So whether this is okay, if you have questions on how to present things, and so that I can assist there. This is not mandatory. If you decide, so I don't need this, that's fine. But if you don't have a lot of experience with giving talks, maybe even in English or about a topic that you are not so familiar with, then this is something that I would recommend. So if you decide that's something that could be good for you, then please plan in this additional week or so to be in a presentable shape, like 1 week before your actual date. Okay, but so far 4 people filled in the doodle poll, but I think last week like 7 or so, 6, 7 mentioned that they are interested in. So please like take a look at the doodle poll. So let's take the doodle as the reference for when will we have talks in the Q&A session. Good. I also added 2 additional papers to the website as possible topics. One is very brief from 1970 and should probably get a second paper to do something like a historical comparison. So what was done in 1970 and what can be done nowadays. So I will look up some reference if you're interested in that. Then I have here a reference that may be interesting to some of you if you want to take a closer look at MHD simulation. So this is an open source MHD code. And if you want to play around with something like this, there are others around. So just Google it, but this is something that I stumbled upon and wanted to share here. Link is also in the chat. Good. So for today, I have prepared, I want to repeat the like the exercise from last week, namely that I provide you with a question, and then you have like a few minutes, 4 or 5 minutes or so in a breakout room to discuss this, and then we have a brief poll here using the Zoom polling that you can give your answers. And for that, wie machen wir das denn am dünnsten? Okay, so let me do it like this. I copy this in the chat so that you have it available while you are in the breakout rooms. Oops. So the first question is on the need for magnetohydrodynamics, and is asking about under what circumstances it is possible to ignore all the magneto part from the hydrodynamics. So this is the question here. In which cases can we stick to pure hydrodynamics to describe the motion of some gas? And I give you here 4 possible answers. And you can also give multiple answers. So if you read the notes, if you have them handy right now, this is something that you should be able to answer. And let's just do 3 breakout rooms. And after 5 minutes, I will close the rooms if you're not finished already, and then we can do the first poll. Okay, and so just to give some feedback, let me start the poll. Unfortunately, I added all the questions to one poll, so just hand in the answer the first one for the moment. The others we should discuss in the next breakout sessions. So that should be here. So just look at question number 1. Everything else we can ignore.
Ich glaube aber, ohne die anderen Fragen zu beantworten, kann man das nicht eingeben.
Entschuldigung? Funktioniert nicht?
Nee.
Das heißt, Sie können nichts eintippen, oder was?
Ich glaube, man kann nur auf Eingeben klicken, wenn man jede Frage beantwortet hat.
Dann ist egal, was Sie bei den anderen machen. Just type in some random stuff for the other questions, and then I will restart this always. And 9. So I think 9 should be good. 9 or should it be 10? I think we lost somebody. Okay, I think I stopped this here unless somebody shouts that he needs more time. Okay. Good. Okay, so let's look at results for question 1. Okay, so I offered 4 different possible answers. No gas ionization. If we have no gas ionization, can we describe the fluid motion with pure hydrodynamics? So 6 out of 9 answered yes, this is an option. Which means 3 didn't choose. What would be the argument to say if we have no gas ionization, we still need magnetohydrodynamic? Maybe anybody can offer an idea? No? Okay. So I would argue that when you have no gas ionization, so you only have neutral particles, and if you do not include any processes that can produce ions, then the presence of any magnetic or electric field doesn't matter for the motion, because the forces cannot couple to the particles. Would anybody argue against this?
No, except in the extreme cases where the magnetic fields are so extreme that the magnetic moment is enough, but I don't think that's the case. Like in Kernspintomographen.
Yes, but what is the effect of the magnetic moment? It produces a Zeeman effect, basically, that splits up energy levels so that the radiation interaction is maybe affected, but the motion of the gas, because in Kernspin, so in MRN, magnet resonance. No, what's the English term? MR. NMR. It doesn't. There are no forces actually acting on the neutrals or charged particles in your body, right? So I would argue if you have no gas ionization, then you don't need MHD. But don't take this for granted. We are discussing here more than, so if you can come up with a good argument why this is wrong, please share it.
Might be weak force, but how is it with magnetic multiples, like if you had hydrogen gas? Water gas, I mean, water vapor.
So you're saying that when you have an electric field, maybe that it can couple to the permanent dipole moment of molecules.
Yes, something like that.
So in this case, one would have to compare the coupling strength for this dipole interaction with the regular Coulomb force. And so correct me if I'm wrong, but I think this is a couple of orders of magnitude weaker compared to Coulomb. 2 orders of magnitude? I don't know. Out so by heart. But for that reason, I would argue you can basically neglect this because all the other processes are stronger. But it's a good point that, of course, when you have dipole moments, they can couple to electric fields. Okay, good. What's with the second question? Second answer option: an overall electrically neutral gas. So 2/3 of you mark this as, in this case, we can ignore magnetohydrodynamics. I would argue that this is incorrect, because if you take a gas, split it in half, and have the 1/2 positive charge particles, or if you take a box of neutral gas and neutral hydrogen and like ionize all the hydrogen atoms so that you have now like the same number of electrons and the same number of protons, the whole box is still overall electrically neutral. But you have like a ton of charged particles that will be subject to Lorentz forces, Coulomb interaction, induction, if it moves, and so on. So in this case, overall neutrality, electrically neutrality, is not a sufficient criterion.
But what about if the gas is overall homogeneous neutral? So you have a good mix of protons and electrons, like a plasma.
Yes, exactly. That's the definition of a plasma. If a plasma, and a plasma is cannot be described with pure hydrodynamics, because in contrast to what we assume for the hydrodynamic case, you now have attracting and repulsing forces between the fluid particles. So this affects the overall motion and the status of the gas. So even if you mix them properly and you stir it, you have suddenly currents in the gas that induce magnetic fields that affect the motion of other charged particles. So I would argue that overall neutrality is not sufficient. But again, this is, don't take everything for granted, what I tell you here. Good. Next question. No external magnetic field is, I think, not enough, because it can still be that we have charged particles and external and charged particles in there, and we can induce magnetic fields in the in our plasma, and we will still have electrostatic forces, so Coulomb forces. So I would argue that no external magnetic field or no external electric field are both not sufficient, because even if you have no electric or magnetic field externally given, it's not sufficient, I would argue. Okay. Any final remarks from your side? the time too short for the breakout discussion? Anybody wants to have it longer?
Yeah, I think it was a little short. I prefer to have some minutes more, maybe like 2 more minutes.
Okay, good. Before I forget this, because I checked my email, so could at the end you, Frau Grünwald and Frau Krasilowskaja, please stay, because there's an overlap between the presentation topic, and maybe we can arrange something.
Oh, okay, sure.
Okay.
Yeah. Cool. So okay, so let I think you cannot see. So I copy the next question. Let's see. Oops, how do I do this?
Is it just the second question of the poll?
We can do the second question. I was thinking about maybe reducing the question count, because if you want to discuss a little bit longer, and I don't know whether you can see the poll while you are in the breakout room. So okay, so let's do question number 3, the coordinate transform. Again, I copy it in the chat as additional reference, so that you can look it up while you are in the breakout room. So the question is on the coordinate transform that we discussed in the lecture, which forces only occur in the co-moving coordinate system in MHD. Breakout session. Okay, so this seems to stabilize now. So I give it a few more seconds if you want to add your answer. Okay, so let's stop this and share the result. Here. So the question, which forces only occur in the co-moving coordinate system in MHD. And 9 out of 11 chose fictitious forces, also Scheinkräfte. And then a few picked Lorentz and Coulomb forces can only occur in the co-moving coordinate system. So maybe let's start with the third point, fictitious forces. As you know from the lecture, for fictitious forces to occur, you mustn't be in an inertial, what's this English word? Inertial frame of reference, an inertial system. And so if you are in the rest of frame, in the initial reference frame where you are at rest, I would argue that you cannot have any fictitious forces there. But if you want to convince me otherwise, then that would be very welcome.
And depends not only on the observer if there were fictional forces in the rest frame, because if I'm accelerated, but in my frame, in my rest frame, I will see those fictitious forces.
Yeah, but where do the forces occur? And if you are, wait, what you are saying is you have a reference, a frame of reference at rest where you have your fluid motion taking place.
No, it's my reference. I'm the observer and I'm accelerated.
You are accelerated. Yeah, that's what I'm saying. While the fluid is in a different system. Is this what you're saying?
No, I am the fluid.
You are the fluid. And
The
if
fluid
you are
is accelerated.
and
And I'm moving with the fluid.
Yeah, but when you are the fluid and you are accelerated, you are in the co-moving coordinate system, right?
Yes.
Yes. Which means then you can have fictitious forces.
Oh, I see.
But if you are not accelerated and not moving, then then I don't think that fictitious forces are possible there. So what would that be? That's like, I don't know. Centripetal forces, difficult. Coriolis force also not possible, I think. So I think the third point can only occur if you are in the co-moving coordinate system. What about Lorentz forces? Are Lorentz forces only possible in the co-moving coordinate system? The answer is no. When you have two charges as rest at when you have a fluid and you have particles moving in the fluid, charged particles, and you have a magnetic field, you will have Lorentz forces. So even in a non-co-moving system, because yeah, so I think Lorentz forces are possible, and the same goes of course for Coulomb forces, which also work even if everything is at rest and you have two particles, then charged particles, then you will have Coulomb forces even in non-co-moving coordinates. Okay. Again, so open for discussion if you think I'm wrong. And then if not, let's just jump to the last question because no, we do something else. I prepared, let's see. I linked at the web page, and when you look at the lecture notes, you might also see on the first page. Let me share this briefly. Here, so this is the here. This is the first page of the lecture notes, or the second page after here, this one. And there's this image on the bottom right showing a pulsed jet simulation under interstellar gas conditions. This is like a shot from a video showing the time evolution of this pulsed jet. And I want to show this video. What you see here as colors is the density distribution. This is a two-dimensional magneto-hydrodynamical simulation that is non-adiabatic. So energy is exchanged between fluid elements back and forth. It is compressible, so the density changes all over the place. You have heating and cooling via radiation. And you also, they compute the ionization condition of the particles, and I will show this later. So this is the time evolution. Do you see the video?
Yes.
Good. So the jet is coming from the left, and the pulse thing is basically these reddish things. These are like dense gas packages that are coming from this orifice here on the left-hand side, this opening, and moving with high velocity to the right. Red means very high density. Black means very low density, though this is logarithmically scaled. And this light blue is intermediate gas density, so more on the lower density side. And so you see that it is pulsed in the time between two pulses is 22 years. So this is the time scale this is working on. And you basically see the what you see is certain structures are created. You see this pulse is creating like a cocoon, so it plumes out here in these regions, and this is growing. It behaves differently in the top. And this is the result of of all the MHD equations that we had in the lecture interplaying with each other. Like, so you have high density here and you have lower density here. Material is coming in this direction and so on. Now, what I wanted to do, this video is linked once as MPEG file and as animated GIF on the web page. And I also have a screenshot from the paper that I want to share. What's this then? It's I have to find the file. 1 second. Okay. To share it to you. And what I want you to do in the breakout is to like discuss with what you know about fluid dynamics, about thermodynamics. Describe the motion of the jet and describe why certain of these structures, in your opinion, are created. So let's see here. In the chat, I link an image showing this. So let me share this so that you see what I prepared. So this is the image I also upload in the chat. On the left-hand side, what you see is basically the 3 snapshots of this video in black and white encoded. This is from the same video. The density is encoded here in black and white now. And on the right-hand side, you see basically from the same simulation, not the density, but the ionization fraction. So what is the fraction of neutral particles? So everything that is black means it's 100% neutral. Everything that is white means it's basically all ionized. And so you can use this as reference material for your discussion if you cannot look at the video. And please look at these images, look at the video, and try to get a qualitative understanding or a qualitative feeling of what might be going on in this jet. What is the reason for these wings to form at the pulses over time? Why is the material ionized or neutral at some positions? What does this mean for the temperature maybe? And so on. So that's the discussion topic I suggest. And let's end. So it's just to like take your intuitive physical understanding that you have and just apply it to this video. We do it for 10 minutes. And then briefly, 5 minutes, maybe you describe or you explain a little bit what's going on. So let's see, breakout rooms, breakout session, other sessions. Well, we keep the same sessions. 10 minutes, okay? So, good. So this is entirely experimental. So let me share the screen where I let the video run basically. And so what is the result of your discussion? So we don't need to go through the breakout room. So if some of you want to share basically their findings or the results, that would be nice. Or maybe I can ask a couple of questions. So if you look at the jet, you see that the pulse here, for example, and you can see my mouse is very confined, and then it becomes wider here. What do you think? Why is this? First of all, yeah, why is this?
Maybe I can start with the two possible answers and maybe a question. So because if there is, let's say, if we look at this image on the right with where the background is black, so the first question would be like, is it empty or not? If it's empty, then the jet is interacting with the, I mean, maybe the last parts where the jet gets distorted and all, it's losing whatever forces or momentum or something. But if the black part has some environment or pressure or something, then it is going to interact with it. And the first question would be that I would ask myself is that, does the black part has any density or some kind of pressure?
Yeah, I can answer that. So here, so again, here on the left one, where it's more in gray, this
Yes.
shows you the density.
Yes.
And where it's gray here, you have a density of, I think, 10 particles per cubic centimeter. So it's not empty.
Yes.
On the right-hand side, everything that is black means it's 100% neutral, not ionized.
And then if there is a shock wave going along, and then it is going to compress everything in front of it, and that is definitely going to affect, and those might be the changes which we are observing. That's the one way, I mean, but eventually, I know maybe it will depend upon how much or some, yeah.
Yeah, what you see here on the left on the video is when I have at the very beginning, you have here this pulse of material being ejected to the right. And then you have this bow shock structure here forming. So material in front of the jet is being compressed. And it needs to go somewhere because momentum is being injected from this package of material that's coming with Mach 10 or something from the left. So it needs to go somewhere. It's like when you have a snow plow running through snow. So the snow piles up in front of the snow plow, but at some point it goes to the right and to the left because it has to go somewhere. And that's what's happening here. And this creates the boundary here of this pulsed jet. So you have the jet in the center, and then you have like this large envelope here, the Bow-Shock structure that is created by the thing that is running here into the ambient medium. But when you look at this, it's very thin here, and when you follow this package to the right, when you follow this package to the right, maybe to here, it's now not thin anymore. Or here, it becomes wider. And why is this like puffing up here in contrast to in the beginning?
Maybe because the pressure inside this pulse is much, internal pressure much higher than that's of the outside material, and so it expands.
Exactly. Yeah, so you have it's. You also see here in this image, when you look at the right one, that exactly at the position of these pulses, the material is highly ionized. That's because one effect of the shock is that the large amount of kinetic energy and momentum that is colliding with the material here is creating a lot of friction. So there's a lot of heat injected here into the medium. So the material is dense and hot, and consequently the pressure is much higher than in the ambient region. So for example, here, everything where it's black, you have very low density, very little material, and necessarily a low pressure, which means that these pulses expand here in this direction, but they also expand in these empty spaces here, of course. So that's why the material that is pushed out to the top and to the bottom then expands here in this wing structure, so which is just a two-dimensional cut. So at the end, it is basically like a cocoon forming that is carried along. So material is flowing here in this direction and expanding. That's why the density here is much lower than here and here, for example. So that's taking place. You see how this expands when you follow it here. And you see also when you when you look at the first pulse, that because it collides with the material in front, the distance between the two pulses changes. You see this, that the distance is different. And that's because this is decelerated. So at some point, the second pulse is catching up with the first one now. Yeah, and this colliding, you have this denser part that is becoming slower, and from the back, there's a collision with the second pulse, pushing it apart. So that's and running through it. So that's what's taking place here. And then you have here this Bow-Shock structure in front that is like the bow wake of a ship running through a quiet water, creates here this structure because of the superposition of the waves that are created in the material. Yeah, so these are things that take place, and so even though we only have the density here, you always have to, of course, consider how does the temperature change, how does the velocity change, what is with the pressure, the ionization fraction, and so on. So this is in detail explained in the paper by Norman and Stone. That is also linked, I think, on the web page if you are interested in that. Consider this just a toy exercise to take the concept from the lectures and try to make sense of what here this numerical simulation spits out. Because imagine that you are the person that coded this simulation here. How do you figure out whether you did it correctly? So you need to apply it to some test, and one fundamental test is, of course, whether this makes physically sense. As far as a two-dimensional simulation can make physically sense, because there is no two-dimensional world. So yeah, things are dense and hot. Are they expanding? We have a shock wave. A shock wave means fast material is running into slow material, so it's stopped. Does the velocity changes and so on? Okay, so this was this example. If you have things to contribute, just like speak up.
May I ask one question
Yeah.
regarding the snapshots? And I think I have to share my screen if it's allowed to point my cursor exactly where I want to ask the question.
Is the screen sharing still on? No, I think you do I have to allow it? By the way. Okay.
I mean, if I can share it, I can do it from my side.
Yeah, do it.
Okay. So can you see my screen?
Yeah.
So my question is like this. Let's say I am looking at this pulse and then this one and then this one and then this one and also this one. So my question is, these snapshots, are they taken at the same time when they introduced the pulse to the jet simulation, or are they from the different time? Like, because you explained that if you add two pulses and then there's a third pulse and they will catch up differently with each other. And this thing, if I look at...
This is not the same, right?
So the time of the snapshot, is it for... does it correspond to the time of injection of the material or the pulse, I would ask?
Just from looking at the picture, I would argue no, because then the first pulse visible in every image should be the same distance from the opening here on the left.
Yes.
So no. But I don't. I think I don't know. But it actually, yeah. Does it matter?
I mean, for comparing these two images, for me, it would be interesting to see because it matters, like in the sense that if I get this understanding that the injection of the material is happening at the same time, always, like that would what you want to do in the simulation, and then the time where I add the pulse is, let's say, 20 years, and then the second one is 20 years. So then I would maybe make a better judgment that how quickly or slowly these paths are like opening up.
What you know is that every single of these pulses was introduced in a regular periodic interval.
Okay.
And if they are now not equally spaced apart,
yes,
then they change velocity, right?
Yes. So that was just like concern that if I get this, I mean, I suppose I can get that idea from the paper that, yeah, but that would, I thought maybe it would make it easier.
I think that the choice for the times to create the figures here was because to highlight certain structures that form and to have like the evolution visible in 4 frames or so.
Okay.
Because you have to make like an informed choice on what to plot, right?
Yes.
Or but this is, on the other hand, this is also subjective. So if you think, yeah, you could have also chosen different times, I guess.
Yes.
Okay, so it's okay if I stop this?
Yes.
Oh no, this was a meeting stopping. Okay, good. So final poll that I briefly come up with, just as anonymous feedback for this like modus operandi that we had. Whether you think this is useful, sufficient, you want more of that, longer, shorter, I don't know. Good. Just to show you the results. So, okay, the majority thinks this is okay-ish in the sense of we don't need significantly more or less. There are some minority opinions here, so I will try not to overdo this. Only one argued that he wants to have less than 5 minutes. 5 minutes is frequently mentioned as the like maximum time for these discussions to like limit this and bring it back into the large circle before it basically diverges into no man's land in discussion. And of course, this depends on how good you read how well you read the lecture notes and how well I chose the questions. Okay, good. But this is just for me as a brief thing. With this, I think we stop here. Thanks for coming. Also, and Frau Grünwald und Frau Krasilowska, dass wir nochmal sprechen, bitte. Also, dass Sie bitte noch drin bleiben. Und für die anderen, to the rest of you, thanks and see you next time.
Hallo.
Okay, so, da sind wir unter uns. Sehr schön. Eine Sekunde.